There's a worldwide network of atomic clocks, and they're regularly compared. They're located in different places at different altitudes. Ours in Brunswick is 200 feet above sea level, while our colleagues in Boulder, Colorado are 5,000 feet up. There'd be no point in comparing the clocks if we didn't take the effects of relativity into account.
The atomic clock has been up on the Zugspitze, Germany's highest mountain, for 4 days. Now it's back down on the flat and on its way to Brunswick. We hope that the sensitive chronometer will survive the return journey unscathed. The clock is still running. Andreas Bauch connects it up to a measuring device and compares it with the clock that stayed behind in Brunswick. Just as Einstein predicted, the clock from the mountaintop is 119 billionths of a second ahead of the one that stayed at home. So time really is relative, a fact that galvanizes the imagination of science fiction authors to this day. They manipulate time, dilate it and contract it, send their space crews to galaxies light years away, and even confront them with black holes.
Was sagen die Detektoren?
Es sieht gut aus. Ich messe starke gravimetrische Wellen.
Hinweis auf ein schwarzes Loch?
Es ist direkt vor uns.
For our astronauts, a black hole is both hazardous and intriguing. On the one hand, they might get sucked in. On the other, time goes more slowly the nearer they get to it. Is our ensign heading for a source of eternal youth for all astronauts? Scientific theory tells us that in black holes, physical mass is concentrated in an incredibly small space. The attraction is so strong that time is dilated to an extreme degree. So, is there a chance of eternal life after all?
Life in the vicinity of a black hole wouldn't be very pleasant. Seen from the outside, life near a black hole would take place in very slow motion. Clocks go slower around black holes. That means we would hardly age at all, because time more or less stands still. The trouble is that the forces exerted on us by a black hole are so extreme that we wouldn't get much benefit from aging so slowly. We'd be stretched into something like a string of spaghetti, and that'd be the end of us.
Einstein loved abstract thought experiments. What happens when a clock is moving fast, say, in a train? His conclusion was, the faster it moves, the slower it goes. If the train could travel at the speed of light, the clock would stop altogether. Einstein's best-known thought experiment is the so-called twin paradox. It goes like this. One twin travels into space in an incredibly fast spaceship. His twin brother stays behind on Earth. The spaceship goes hurtling through the universe for a few decades, almost at the speed of light. The twin back on Earth observes life on board the spaceship and rubs his eyes in wonder. They seem to be taking it very easy up there in space. His brother, the captain, and the ensign all move around in slow motion. Time goes more slowly. From the other perspective, things look very different. The Earthlings are all whizzing around, as if they'd been speeded up.
Das Leben auf der Erde ist offenbar ganz schön hektisch.
So how fast time flies is a question of perspective.
Relativity theory says that a clock moving fast will go slower than a clock that stays put. The two twins are clocks. One twin measures time in relation to the Earth. The other twin measures time in relation to the spaceship. The difference between these two relative systems is the fact that the spaceship accelerates on its way out into space and accelerates when it comes back to Earth. The difference in the two clocks hinges entirely on the fact that one of them accelerated, moved faster, and then came back to Earth. So the accelerated astronaut ages more slowly than his twin brother who stayed on Earth, and therefore was not accelerated.
After 20 years, the spaceship returns to Earth. The march of time has left its mark on the Earth dweller. This scene, made by Einstein, takes place exactly as the relativity script says it should. The Earthling's widely traveled twin brother has stayed remarkably youthful, thanks to the speed he's been moving at. Munich Airport. We're out to prove that fast-moving clocks really do go slower. Once again, we need the assistance of Andreas Bauch and his portable atomic clock. He'll be putting it on board a plane flying to Tokyo and then back again to Munich. But this time, things are not quite so straightforward. Andreas has to take account of two conflicting forces, speed and gravity.
When we put the clock on the plane, it will go faster because of the high altitude. It will also go slower because of the speed it's traveling at. We're familiar with the first effect from the experiment on the mountain. All we need to prove now is that time goes slower at high speed.
The plane is waiting on the runway. 20 minutes to go before takeoff. Lufthansa flight captain Paul Uffer knows what's coming.
Ich sehe, der Herr Dr. Bauch kommt rein. Herr Dr. Bauch, guten Tag, willkommen an Bord.
Dankeschön. Ja, das ist das gute Stück.
Ich nehme gerne Ihre Uhr in Empfang. Sie wird dann gut versorgt bis nach Tokio.
For a second time, the atomic clock goes up in the air for us. 11 hours out and 11 hours back. Average speed, 900 kilometers per hour. Average altitude, 10,500 meters. Both factors have an impact on the functioning of the atomic clock. After landing in Munich, the cesium clock is immediately taken to Brunswick. It had been specially primed for the experiment beforehand.
We modified the clock to ensure that on board the plane, traveling at an altitude of about 30,000 feet, it would go just as fast as if it had stayed in one position on the ground the whole time. Now that it's back, we can see the effect of the motion. On the plane, it went 25.9 billionths of a second more slowly than if it had not been moved at all.
Here's the result of the measurement once again. Traveling on the plane made the clock go 25.9 billionths of a second more slowly. In his theory of relativity, Einstein demonstrated convincingly how motion and gravity affect the way clocks tell time. But does this make any difference in normal, everyday life? The surprising answer is yes, it does. Without Einstein's theory, no driver finding his way around with the help of a car navigation system would ever get to his destination. The car navigation system hinges on satellites of the Global Positioning System, GPS, with atomic clocks on board. A global network of 24 satellites beams the present atomic time to Earth at the speed of light. After a few hundredths of a second, the message arrives at the car's navigation device.